One second. Okay. Okay, well, let's start the lecture for today. Today, we're going to come back to a question that we actually asked or promised that we would ask on the very first lecture of the course, where I mentioned that we're going to talk about a number of different algorithms in this course, and we're going to talk about some principles that we use, like maximum likelihood and MAP, as the basis for training learning systems of different kinds. And that we were also going to talk about the question of, are there any fundamental laws that we can come up with that govern the learning behavior of any learning system, including your brain and mine? And so today I want to, we're going to cover an area that's called computational learning theory. This is actually a very active topic within machine learning that warrants its own annual conference. There's a conference on learning theory, COLT. If you look online, the online proceedings of these conferences from year to year are all available for free online. So there's plenty you can look into. But fundamentally, the question we're going to ask today is this one. What are the general laws that constrain inductive learning? That is, function approximation, let's say. We're given examples of the input-output of some function, say from x to y. We want to estimate what that function is from examples. And so we're interested in, can we come up with some theoretical analysis of that problem that relates the number of training examples that we provide to the learner to the probability that it's going to succeed, where we define success in terms of the error rate that it'll make on future examples when it has to make new predictions. And it turns out that it's also going to be related to the complexity of the hypothesis space, or the class of models that the learner considers. And it's also related to how it gets its training data. So just to get ourselves to think about this a little bit, here are three somewhat different questions we can ask of this ilk. The first one says, well, all of these have to do with a scenario where there's some function we want our learner to learn. We're going to call this C. It's a function from some input vector of features x to a Boolean valued y, 1 or 0. We'll call these concepts in meaning a Boolean valued function. And so think about it this way. We're going to provide training examples of C, that is inputs and their labels, x's and y's, to the learner. And we'd like to know how many training examples are sufficient to succeed. And here are 3 different scenarios we might consider. So, like for example, we might consider the problem of classifying students according to whether they are, let's say, computer science major. We have some features we're looking at. We have a probability distribution. Maybe let's say we're interested in classifying students who come in this door. And randomly people come in this door. That's going to define the X's that we're interested in. Now we just want to classify them according to whether they're computer science majors or not. So one scenario we could have is that the learner, we have a learner and we have a trainer. The trainer knows C. It knows the function, we assume. And so it can label, it can, for any X, it can tell us what the Y is, computer science major or not. That's what the trainer can do. And we also have a learner who's getting these training examples and trying to estimate what the function is. So one scenario we could consider is that the learner proposes instances. The learner says, what about this student? And then the trainer says, no, not a computer science major. And then the learner says, can pick any other student they like. They don't have to take the ones that are coming in the door. The learner maybe could optimize by choosing the student that they think will somehow give them the most information. Right? So that's one scenario, we'll call it a problem setting, in which we could consider this question. So we could consider the question of how many training examples will it take to learn successfully if the learner gets to choose an arbitrary X out of the space of possible X's and ask the trainer, what's the correct label for this X? And under that setting, we could consider the question of how many X's will the learner have to ask about in order to succeed. That's often called the active learning scenario, where the learner gets to choose the X's and then a trustworthy trainer will label them. Scenario 2 is kind of the flip of that. What if the teacher gets to choose? What if the teacher who knows the function we're trying to learn is trying to teach in the fewest possible number of examples? Then given that the teacher knows what the criteria are, like whether you're carrying a laptop and whether it's an Apple or a PC might be a relevant feature, whereas the color of your hair, probably not. And so the teacher who knows exactly what that function is might be able to construct a particular collection of examples that very efficiently communicate what the decision criterion is, what the function is. Okay, so that's a different setting. A third one, and the one we're going to talk about today, is the one that we were just experiencing, where we say it's neither the student nor the teacher who picks the next example. Instead, there's some underlying probability distribution, let's call it P of X, that determines the probability that any one of the possible X's will appear. And we could just watch people coming in this door. That's a draw from P of X. And instead of having the student choose which X we'd label next, or having the teacher choose which X we'd label next, we'll just take the random distribution of X's that appear in our doorway, and the teacher will still label those correctly. But now, that's not the active learning scenario where the student chooses. It's not the training scenario where the teacher chooses. It's just examples are coming in from some underlying P of X distribution that might, it might not be a uniform distribution. For example, it might not include very many 5-year-olds, but include a lot more 20-year-olds, for example. But there is some P of X. And so we're going to consider this. What if the examples are generated by some random process, P of X, that proposes instances, and then the teacher labels each P of X that comes each x that is drawn from P of x. So that's the scenario we're going to consider. And now in this scenario, it turns out we're going to be able to say some pretty interesting things about how many draws from P of x, how many training examples the learner gets to see, the complexity of hypothesis space that it considers, and the probability that after seeing, let's say, m of those examples labeled by the teacher, the probability that the learner will be able to output a hypothesis whose true error is less than some bound epsilon. So we're going to be able to say something quite quantitative about that. So that's kind of where we're headed today. All right, now you may recognize this big picture. We talked about it before. I decided I would show it again just to get us thinking about this problem in an appropriate way. So when we talked about this big picture before, we were just pointing out that for any kind of function approximation problem we're solving, we can think of the setting as we have some set x of instances. They can be labeled positive or negative. We have some other set of hypotheses that we can consider. Maybe it's all decision trees, or maybe it's all logistic regression functions with all possible parameter values. But then there's this, correspondence between any one of the h's that we might consider and its corresponding labeling of x, right? For any hypothesis we choose, when we talked about it before, we were talking about decision trees, so let's continue that way. For any decision tree that the learner might choose, that imposes some labeling on x. It'll assign every point in x either plus or minus 0 or 1 label. And when we talked about this big picture, we had this little discussion where we asked, well, if we only get to see some of the labels, the space of all possible x's may be very large. The space of all possible humans who might be students could be very large. We only get to see some of them labeled as computer science majors or not. And we asked the question, we use this big picture just to notice that for any particular set of labeled examples that we do have, like these pluses and minuses shown here, there might well be two alternative hypotheses, both of which perfectly agree with our labeled subset of x. For example, there could be two decision trees, both of which correctly label the positive examples positive and correctly label these negative examples negative. And we had this little discussion about, well, how many labeled examples would we really need to provide in the case of decision trees? We talked about that. In order to be guaranteed that our learner would be able to shrink its choice of hypothesis down to just one unique decision tree. And we agreed that, well, because decision trees have this property that you can represent any Boolean valued function over discrete valued x's, then we'd really need to see every instance labeled in order to have just one decision tree uniquely left that would perfectly fit the data. Right? And then, and that was just because we can represent any Boolean function, any labeling of the x's with plus and minus using, there will be some decision tree that will correctly capture any function or any labeling of x. Because of that, we agreed we'd need to see labels for everything if we really wanted to get down to one. Okay, so why am I talking about this? Because this is the kind of thinking we need to do if we want to discuss the question, how many training examples are we going to need in order to guarantee that the hypothesis output by our learner has some bounded error. Okay, and actually the discussion we had before was just the extreme case of that, where I said, I want an error of 0. And then we agreed, well, you're going to have to see all the examples in order to get an error of 0. But now we're going to weaken that in a couple ways. We're going to say, well, what if I don't see all the examples? Is there any kind of guarantee you can give me? And we're also going to generalize it by not looking just at decision tree learning. In fact, we're going to look at what I'll call consistent learners today. A consistent learner is one that outputs a hypothesis that perfectly labels the training examples we've seen. It's consistent with the training examples. And if there is such a hypothesis available, then it outputs a hypothesis consistent with the labeled examples that perfectly classifies them. And now that doesn't have to be just a decision tree learner. It could be a logistic regression learner. It could be any kind of learner that we want to make up that's a consistent learner that finds if a hypothesis exists that could perfectly label the examples, that's what it's going to output. We're going to talk now about any consistent learner, looking at M labeled examples where P of X is the source of the X's, and then a perfect teacher labels those. And now we're going to ask the question in that setting, what can we say about how many examples you see, the complexity of H, and the probability that you're going to learn a hypothesis whose true error is at worst epsilon, given that its training error is obviously 0 because you found a consistent hypothesis. Uh-huh.
Yeah, when we talk about the consistency of a learner, do we need to know the data?
The question is, when we talk about the consistency of a learner, do we need to know the data? The answer is not really, but we are going to make the assumption, and the theorem that we're about to prove assumes that there is a hypothesis that can perfectly label the training examples. And that the learner is considering a space of hypotheses that includes that.
So a learner is called consistent if and only if that's given that there is a hypothesis
that can perfectly label the example. That's right. Right. So a learner, how could we have a learner that's consistent? Well, it's going to have the hypothesis, it's going to have to be able to express the hypothesis corresponding to the function that the teacher is actually teaching. And it's going to have to be able to find it, too.
If for some cases it can find the optimal, the perfect hypothesis, and in some cases it can't, then it's not consistent.
Right. If there is no, well, we're going to prove we're going to talk about a series of theorems. The simplest one, and the one that we're going to prove today, applies only to a consistent learner. And a consistent learner is one that outputs a hypothesis that perfectly labels all training examples. Then we're going to see that you can weaken the conditions of that and talk about bounds, even in the case where there is no hypothesis that perfectly fits the data, and the learner simply outputs the best fitting one, the one that labels the greatest number of examples correctly. Okay. But the first theorem we'll prove is just in the slightly more restricted case where we assume you can't output a perfect hypothesis. Okay, so to be a little bit more precise then, here's the problem setting we'll consider. We have a set of instances X and a set of hypotheses H, just like we talked about. A set of possible target concepts, we'll call that C. That's just a set of functions that the teacher might try to teach us. And actually, y in this case we're going to assume is just 0, 1. We're assuming it's a Boolean function. Okay. So the C is the set of functions the teacher might try to teach us. We'll assume the training examples are generated by this fixed probability distribution. We'll call it D. That's just our p of x. And we don't assume the learner necessarily knows what p of x is. We just assume there is some p of x. People are coming in the door. There is some distribution of people coming in the door. We might or might not know what that distribution is, but we assume it exists. And furthermore, the training data are drawn from p of x, and so are the future examples that we're going to test our program on, also drawn from the same p of x. Okay, and so now, given that, our setting is that the learner observes a sequence of training examples of particular instances of x drawn from p of x and their correct label, so that's c of x. And then the learner must output a hypothesis, which is its estimate of what the function is. And now we're going to evaluate that hypothesis, how accurate it is, simply on subsequent instances drawn from that same p of x. So notice this means that there's randomness here in which x we see, but there's no randomness in what the label is. We're assuming the teacher always gives this. If we see the same student twice, the teacher will always say the same label for that student. There's no randomness in that there's noise in our labels. The labels are deterministically related to the x's. The randomness comes in because p of x is going to give us some random sample of training examples. Okay? All right, so that's our setting. And now, to make our question well defined, we need to talk about the true error of a hypothesis and its training error. So what do I mean by the true error of a hypothesis? I just mean the probability that it's going to misclassify the next instance drawn at random from p of x. Okay? Has nothing to do with, well, I shouldn't say it has nothing to do with the training error. It's a different notion from training error. If I have a hypothesis and there's some function c, and I have a p of x, I'm going to define the true error of the hypothesis h with respect to this distribution d, which is p of x. It's just the probability that h will misclassify an instance drawn at random from p of x. Okay? So if I have a hypothesis, the next student who walks in, the next draw from p of x, this is just the probability that my hypothesis is going to misclassify the next randomly drawn x. Mm-hmm.
The number of elements in your training set approached your entire space of x, would your training error approach the true error?
Right. So the question is, if the number of training examples approaches the size of x, will the true error approach the training error? For a consistent learner, it will, right? Because for a consistent learner, that's going to, what it means to be a consistent learner, again, is that it's going to output a hypothesis that perfectly labels the training examples. And as we agreed when we had our big picture discussion, if you get to see every instance of x as a training example, then you're going to be able to zero in on the hypothesis that is the correct function. So this training error will, so as you can see, is if our training set included every point in x, then, and we have a consistent learner, then the true error is going to be 0, and so will the training error. Okay, so that's the true error. Now we want to contrast that with the training error. The training error, of course, is just the fraction of training examples that the learner incorrectly labels, which, of course, for a consistent learner will be 0. But more generally, what we're interested in here is, given the training error, what can we say about the true error of the hypothesis? That's really the heart of our question. We want to know what's the relationship between these two things. And in particular, can we bound the true error in terms of the training error. And in this case of a consistent learner, there's just a special case where the training error is 0. And so can we somehow say, if you get a 0 training error after you've trained on m examples, can we somehow bound what your true error is going to be? And you already know, because we just noticed, that if m equals the size of x, the number of instances that can be described in our instance representation, if we see every one of those as a training example, then we can bound, and we have a consistent learner, then we can bound the true error. It's going to be 0. But the more interesting and practical case is, what if we don't get to see every one of those training examples? Then what? And that's where we're headed. Okay, so before we prove this together, just want to notice, a lot of you have had courses in statistics where you report on some experimental result, and then people ask you to put a confidence interval on your result. And this question we're asking is somehow related to that, right? So let's think of it this way. If I give you a hypothesis and a set of test data that was not used, that's drawn independently from the training data that I used in forming the hypothesis. I give you a decision tree that I trained using this data, and I have an independently drawn set of test data. And let's say there are 100 points in that test set. And you measure how well the decision tree does on that, and you say, well, it got 90 out of 100 right. And I ask you, what's your maximum likelihood estimate of the true error? You'll say, I hope, 0.9. But then if I ask, well, how sure are you of that? Intuitively, of course, you'd say, well, I'm more sure than I would have been if you only gave me 10 instead of 100 examples. But I'm less sure than if I saw it get 900 out of 1,000. So how sure I am about that in the confidence interval on my estimate of the true error of 0.9, of course, is a function of how big the test set is. And when you took that statistics course about confidence interval, you probably saw a formula like this that said, well, the true error, if you have a test set of independently drawn examples, is just that observed test error on the data set D, the test data set D, which was 0.9 in our 90 out of 100 example, plus or minus some amount that varies with n, the number of examples in the test set. And so if I give you only 100 test examples, we'll have one confidence interval here. But if I give you 1,000 instead of 100 examples n, then that confidence interval will be tighter. Right? And you've probably all had this in earlier statistics courses. And if the question we wanted to ask was about what's the relationship between the true error, this is the training error, but if we asked it about the test error, test set error, then we would just use this. We'd have no need for additional discussion. But we do have a need for additional discussion because the question we're asking is, can we bound the true error not in terms of the test error, but in terms of the training error? And of course, H is not drawn independent of those training examples. That's why we get overfitting problems. Remember, overfitting is just this phenomena where the training error that we can achieve is much better than actually the true error, the test error. And of course, the reason is we're using the training data to assemble our hypothesis, to assemble our decision tree, or to pick the parameters of our logistic function. And therefore, we can't trust the performance of that hypothesis on the same training data as an unbiased estimate of its true error. Right? So we need to do something else. We need to derive some other rule than this one that we could have used if we had test data. Okay, so let's do that. So I need to define a little bit of terminology, very straightforward, then we'll prove this. Then we'll ask a question for the one we want to prove. So I'm just going to say, we talked about a consistent learner. That's a learner who outputs a hypothesis consistent with the data. I just want to be precise. A hypothesis H is consistent with a set of training examples if it labels every one of those correctly. And furthermore, given a set of training examples, I'm going to define the version space of hypotheses with respect to some set of training examples D is just the set of all hypotheses that are consistent with the training examples. Okay, so if I give you some hypothesis space H, like all decision trees, defined over the variables of X, and I give you a particular set of training examples, then just like our big picture pointed out, there could be multiple decision trees that perfectly fit this sample of training data that we have. And we're going to call that set of all decision trees or all hypotheses that are consistent with the training data so far. We'll call that the version space. It's just the set of consistent hypotheses. Okay. So now here's the thing. Well, there's that big picture. Can't get away from it. So now here's the thing we want to ask. The question we wanted was, can we somehow bound the true error of a hypothesis based on this training error? We're considering this special case where the training error is 0. We have a consistent learner. It's going to output a hypothesis with 0 training error. And so now we want to know, can we bound the true error of a consistent learner based on how many examples it has trained on? And to do that, the notion that we want to zero in on is this. So here's the set of hypotheses, and there's the subset of them, which is the version space, with respect to some set of training data D. That is, the version space, again, is just the set of hypotheses that are perfectly consistent with the training data D. And so they all have what training error? 0. But what true error? We don't know. Right? Just because a hypothesis is in the version space and it has 0 training error for a particular training set D, we don't really know what the true error is. So I might have a point in there that has, I'm using R to mean the training error here. So of course, every point in this version space will have training error of 0, but it might have a true error that's non-zero. It just happened to get lucky and it got all the training examples right. We haven't seen enough training examples to show that it's going to be wrong on some other student who hasn't yet appeared as a training example.
What was the value of epsilon?
Yeah, so we haven't talked about epsilon yet, but what I'm going to say, so now epsilon, let's say epsilon is some number between 0 and 1. It's some error that we would like to bound. It's some bound on the error that we're willing to tolerate. And so we'll say the version space is epsilon exhausted with respect to the target concept and P of X. If every hypothesis that's in the version space, that is, every hypothesis that's perfectly fit the training data D, actually has a true error less than epsilon. Okay? So for the version space I've drawn here, we could say this is epsilon exhausted, however, for epsilon equals 0.2. Oops. Greater than 0.2. Less than 0.2. Greater than 0.2. Okay? Because it has 2 hypotheses in it, one of which has true error 0.1 and which has 0.2. Of course, they all have 0 training error, otherwise they wouldn't be in the version space. That's the definition. But it's epsilon exhausted with 0.2. Now, why is this an important notion? This is important because we want a result that applies to any consistent learner. And a consistent learner is going to output some member of the version space. We've defined the version space to be the set of consistent hypotheses. And you might have a learning algorithm and I might have a different one, but if they're both consistent learners, they're both choosing among the hypotheses that are in the version space. And you might have a different algorithm, so you might choose a different one than I would choose. But if we know that the version space is epsilon exhausted, that is, everything in the version space has a true error of at most epsilon, then we can say, and if we can somehow get a bound on epsilon, which we're about to do, then we can say, good, any consistent learner is going to achieve this bound because it's choosing among the hypotheses in this version space. Okay, here's the result. Very nice result. If we have a hypothesis space that's finite, has a finite number of hypotheses, let's say like all decision trees defined over instances with 10 Boolean variables x1 through x10. There's a finite hypothesis space. And D is a sequence of m independent examples drawn from P of x and labeled by our teacher. Then for any epsilon, the probability that the version space with respect to Hn, the training data D, the probability that it's not epsilon exhausted is less than this quantity. The probability that it's not epsilon exhausted. That means the probability that there's a hypothesis in there whose true error is actually worse than epsilon. The probability that that can occur after we see m independently drawn training examples from P of x is at most this quantity. And you see that quantity is decreasing exponentially with the number of training examples we see. And it's getting worse the larger the set of hypotheses we consider. And both of those make really good intuitive sense, right? If you only are considering depth 2 decision trees versus arbitrary depth decision trees, and you can find a consistent hypothesis, then you're probably going to need fewer examples. It also is decreasing exponentially with epsilon, the error bound that we're willing to tolerate. All right, so let's prove it. Too many side notes. Let's prove it. Okay, so we want to prove is that after our learner sees m independently drawn training examples, the version space will be epsilon exhausted. Put another way, any hypothesis out of H that happens to successfully label every training example, every one of the hypotheses that can label the examples correctly, has a true error at worst epsilon. That's what we have to prove. Okay, so let's do it. Let's assume we have our hypothesis space H, and our instance is x, and we're learning some function from x, this Boolean function. Okay, so now, and I have m labeled examples. Okay, so now to get started, let's think about the whole hypothesis space. And given these m labeled examples, let's say that well, even without looking at the M-labeled examples, let's just look at the hypothesis space and the function we're trying to learn. Now, some of these hypotheses have 0 true error. I guess one of these hypotheses has 0 true error. Others have true error, 0.1, others have 0.9, and so forth. Let's just think about the set of them that have true error worse than epsilon. So we have error-bound, error tolerance, let's call it, epsilon. Okay, so now let's I'm just going to label those hypotheses that are bad. I don't even know how many of them there are, so I'll label them H1 through HK. Let's let those be the hypotheses with true error worse than epsilon. Okay, those are the only ones we really care about. And what we want to make sure is we want to know how many training examples we need to provide to the learner in order to reveal the high error property of every one of those K bad hypotheses. That's what we really need to zero in on. Okay, so let's say there are K, we don't really know what K is, but there are K hypotheses out there in the hypothesis space that secretly have true error worse than epsilon. So now I ask you, what's the probability that one of these, let's just look at H1. So one of these hypotheses who has true error worse than epsilon will be consistent with the first training example. Okay, what is the probability that it will be consistent, given that it's one of these bad ones that has a true error worse than epsilon? What's the probability that it will correctly label the first training example? Right, it's true error. 1 minus its true error will be the probability that it will correctly label it, and its true error will be the probability that it doesn't. We don't really know what its true error is, but we know it's at least epsilon. Okay, so that probability is going to be at most 1 minus epsilon. Okay. If we say epsilon is 0.2 and H1 has a worse error than 0.2, then for that new example with probability at least 0.2, it's going to mislabel the first example, and therefore with probability 1 minus 0.2 at most, it's going to correctly label it and sort of sneak by undetected as a high error hypothesis. Okay, now what's the probability that H1 will be consistent with, let's say M, independently drawn examples? Right, so now M students walk in the door drawn from P of X. We know that for the first one, the probability is that. What's the probability that this same H1 will sneak by and happen to label correctly all M of the independently drawn students who walk in? Right. Right. These are just independent events. So if the probability that it labels one example correctly is that, the probability that it labels M of them correctly is just that to the M. Good. All right. So now, of course, what we want to know is that the entire version space is epsilon exhausted. So what we're really interested in is the probability that any of these K bad things will sneak by. Furthermore, we don't know what k is. But we know k is, at most, the size of h. So if I ask you, what's the probability that at least one, suppose I do know k, one of these k hypotheses will be consistent with m independently drawn examples. Okay, if there are k of them, what's the probability, what's the bound on the probability that at least one of them will sneak by undetected for being a high error hypothesis? It's a little ugly. It's hard to get a general bound on this, but surely it's bounded by this. Right? The sum of the probabilities is a bound on the probability that any one of them will sneak by. The reason I say this is ugly is that number, if k is big, that number could be bigger than 1, and so now we've bounded our probability by some number bigger than 1, which is a little discouraging. But still, at least you got to agree with me that if I have k independent things I'm testing, the probability that at least one of them will be true is no more than the sum of their individual probabilities. Right? If they were disjoint events, it would be exactly their probabilities. But if they're overlapping events, it won't. Okay? All right. And now, of course, we don't know k, but we do know that, of course, k is at most h, the number of hypotheses in h. And so here's a bound on the probability that at least one of the k bad hypotheses, where we don't even know what k is, but we know it's at most every hypothesis, will be consistent with m examples. And that's the theorem. We just proved it. Okay, and we can rearrange the terms here using, there's a little truth about numbers that says if you have some number between 0 and 1, then it turns out to be true that 1 minus that number is less than or equal than e to that. And so if we apply that here, then we get exactly the form that we saw the theorem in the previous page. Which is exactly what we saw here. Okay, so you've just proved this very fundamental theorem that applies to any consistent learner. Could be a decision tree learner, could be a rule learner, could be logistic regression learner. So long as your learner outputs a consistent hypothesis, if one exists, then your learner will follow this. In fact, if your brain outputs a consistent hypothesis, if one exists, your brain will follow this as well. It's just a statistical property of a consistent learner applied to m independently drawn examples in this kind of problem setting.
Does a hypothesis take any particular form, or is this just kind of an abstract concept?
Right. So the question is, does the hypothesis take a particular form? This result is so general that it can apply. Well, we can apply it if we want to decision trees. We can apply it if we want. It's a little harder to apply it to logistic regression. Do you see why?
The hypothesis space is continuous.
Right. So the hypothesis space has an infinite number of straight line decision surfaces in the case of logistic regression. So you can't really apply it yet. We'll extend this so that we can to logistic regression. But we can apply this to any learner that has a finite hypothesis space, like decision tree learner, rule learner. Uh-huh.
Are you assuming in your M that you're not drawing the same example over again?
No, this is with replacement. So we're assuming that really these are M independent draws from P of X. So you could see the same example twice, which wouldn't help you. So it's, but that's what we're assuming here. You know, if you think about the steps we just went through, that's implicitly the assumption. Okay, so now let's play with this a little. So what does this mean? This really means is, you know, the probability the version space is not epsilon exhausted is bounded by this expression. Well, that's just the probability that there exists a hypothesis such that it achieves 0 training error, and it still has a true error worse than epsilon. And that probability is what we've just bounded in the theorem that we just proved. Okay. Now, suppose we want to use this to choose the number of training examples to provide to our learner. Well, we can say we want this probability to be at most delta, and then we can rearrange it and solve for what M would be. So if we bound the probability that this will be epsilon exhausted by, say, 0.1, then we can, and we want epsilon to be true error to be at worst 0.01, then we substitute those numbers, we can solve for M. How many training examples suffice to guarantee that with probability 1 minus delta, the output hypothesis, which is consistent with the training examples, will have true error at worst epsilon. Or we can flip it around and solve for other things. If we want the true error to be, if we want to know a bound on our true error, we can put in the number of examples we've seen and delta and solve for that. Okay, now test yourself. Tom's talking about the probability that the learner will output a hypothesis. What's that probability defined over? Anytime you hear somebody talk about a probability, there should be an automatic response in your brain that says probability over what event space? What are we talking about? Probability. What's the experiment that I'd repeat over and over to get to observe that with that probability the outcome is as promised? So when I say here, and what we just proved, that given M training examples, the probability that the learner will output a hypothesis with true error worse than epsilon, despite having 0 training error. What do I mean by that probability? What is the experiment? Suppose that probability is for some values of epsilon and M, suppose the probability is 0.01. What's the experiment that you would rerun 100 times where you'd expect it to succeed 99 times and fail once?
Different draws of data?
Yes, different draws of training data. So the probability is taken over different random draws of training data of size M. And each one of those training data of size M, each of those sets is generated according to the problem setting we discussed. That is, we take a 100 points IID from P of X, independently, identically distributed according to P of X. The teacher labels them truthfully, and that's a training set. Now we train our learner. We could measure its true error, write it down. Now we repeat the whole experiment again. We get another set of 100 examples. It might be a different set, of course. Still drawn from P of X. But, you know, it'll vary. It'll be different. We train our learner. We measure the true error of the hypothesis it outputs. We write that down. If we repeat that experiment 100 times, and our bound says that the true error will be less than 0.1, then we expect the number of times that we observe a true error out of 100 repetitions of that experiment will be smaller than 10%. Will be smaller than 10 out of 100. Okay, so that's the probability distribution that we're talking about when we say with probability 1 minus delta, our learner, our consistent learner, which is outputting a hypothesis that perfectly fits, perfectly labels those M examples, will output a hypothesis with true error worse than epsilon. Okay. So let's take an example. Let's go back to, well, let's apply it to a very simple example. So let's consider a case where my instances are 4 Boolean features, x1 through x4, and the hypotheses that my learner considers are simple rules of this form. So when it outputs a hypothesis, the hypothesis is a single rule of this form. It says, if the 4 features have values that match this template, then y equals 1, otherwise y equals 0. And the different hypotheses vary only by what this pattern of 4 values can be. And what I mean to say here is that for each value we can constrain that it must be 0, or that it must be 1, or that we just don't care. So this pattern here says x1 must be 0, x2 we don't care about, x3 must be 1, and x4 we don't care about. If our instance matches that pattern, then we're going to label the instance positive, otherwise negative. Okay, so clear what the hypothesis space is. And suppose I tell you that I have a consistent learner for this hypothesis space. I don't tell you what the algorithm is. I just say, don't worry, my algorithm's going to output a consistent rule, one that labels the training examples perfectly. And now I want you to tell me, how many examples do I need to provide it to assure that with 99% probability 0.99, my consistent learner, in fact any consistent learner, will output a rule whose true error is at worst 0.05. Okay, well, we can go back to our formula here. And so all we need to say is that m is at least 1 over epsilon. Okay, what's epsilon here? Yeah, 0.05. That's the error that we're willing to tolerate. Okay, and then we want the natural log of, h. Let's come back to that. Plus the natural log of 1 over delta. What's delta here? With probability at least 0.09. Right? We want to have the probability that it will have error at most 0.05, and delta is the probability, remember, that the version space is not epsilon exhausted. So it's 1 minus the 0.99. Okay, so now we can solve for m as soon as we know what this is. What is this? 3 to the 4, somebody said. That's correct. No, 4 to the 3. 3 to the 4. Thank you. 3 to the 4. Okay, why is it 3 to the 4?
For each variable, we can constrain it to 0 or to 1, or we don't care. That's
Exactly. So this is like some weird trinary numbering system where we have 4 bits, each of which can take on 3 values. So 3 to the 4 possible values that we can take on. Okay, so now what does this turn out to be? I cheated and I solved it before class. The answer is m greater than 180 examples suffices. So if you have a learning algorithm that uses this hypothesis representation, and it outputs a consistent hypothesis given the training data, then I can promise you, if you follow our problem setting of drawing examples according to P of X and having a teacher truthfully label them, that any rule that the teacher tries to teach you, you can learn with probability at least 0.99. That is, if you repeat the experiment 100 times, you're going to succeed 99 of 100 at least. Your algorithm will output a hypothesis with true error at worst 0.05, provided you give it at least 180 of these randomly drawn training examples. Pretty cool. Okay, what if I also solve for a few other things. This is for n equals 4. What if I have x1 through xn? How does this scale with the number of features in my hypothesis space? That's kind of an interesting question. Well, in general, this is just going to be 3 to the n. And so this whole expression is going to, the log, the size of h is just going to be n log the size of h. Oh, sorry, n log 3. My apologies. Thank you. N log 3. Because h will be 3 to the n. And so its log will be n log 3. So that term is going to grow linearly with the number of features we give it. It's kind of interesting. So you notice there are two terms summing together here to give us m. One of them really doesn't depend on h. It just depends on how tight we want that probability of success to be. But then the other term does depend on the complexity of h. And so the more enriched h is, one way we can do that is to add more variables to x. Then the slower our convergence is going to be, the more training examples we're going to need. And so if you solve this for this, so this is for n equals 4. If you solve this for a couple other numbers, I solved it for n equals 10. Then we need at least 312 examples. If I use n equals 100, then I need at least 2,290 examples. But you see, this formula is very interesting because it tells us some of the scaling properties of our learning task. Right? If we double the number of features, instead of using 4, we use 8, the demands here are going to go up linearly in n. All right. Here's another one, decision trees. Let's consider simple decision trees because we're going to have to answer this question for them. So let's consider simple decision trees. I have n Boolean variables in my instances, x1 through xn. And I'm trying to predict some Boolean y, 0 or 1. And let's only use decision trees of depth 2 that use 2 variables. So in other words, my decision tree is going to look like this. I'm going to first choose some xi, which might be 0 or 1. And then after that, I'll choose an xj. And I'm going to use the same xj of both nodes in here just to make the arithmetic simple for us. And now I have 4 leaf nodes. And of course, I can label those leaf nodes. That's where I make my prediction of y. So I could label those, whatever I want. Maybe I say this leaf is y equals 1, y equals 0, 0, 1, whatever. Okay, so let's consider H as the set of all such depth 2 decision trees that use 2 variables. And I want to know, again, how many training examples do I need to provide? How many training examples do I need to provide? to guarantee the same kind of bound. So how many trees are, so again, I'm going to just use this formula. We've already decided what we're going to plug in for epsilon and for delta, and what we need to do now is solve for the complexity of our hypothesis space. So how many trees are there like this? It's actually not that hard to solve. So I have n variables, so it's n choose 2. How many ways are there of choosing 2 out of n variables? And then for each of those, I'll get a tree structure, but I won't yet have labeled the leaves. And how many ways are there of labeling the leaves? I have 4 leaves. 16 ways of labeling the 4 leaves with 1 and 0, right? Right? I have to write down 4 1s and 0s. There are 16 ways of doing that. Okay, so that's the number of hypotheses. N choose 2 is actually easy too. That's just n, how many things can I choose for the first thing, times n minus 1. How many I can choose for the next one. And now I've double counted, because I could have chosen them in the other order. So I multiply that by half. And then I have to multiply the whole thing by 16. Okay, so that's just an expression for n choose 2 for this case. Okay, so that's the size of my hypothesis space. Yeah, that's why I wrote it that way. I said xj and xj. So I'm going to just make those the same. We could consider this other more complex hypothesis space, but I don't want to do it in real time because the arithmetic is harder. But that would be an excellent practice question. It's actually slightly too messy to put on a midterm, but it's still a good one to test your understanding. Okay, so now, actually this is easy. I could cancel out the 2 and make this an 8. So now I have a really simple expression here. It's just 8n squared minus 8n, right? That's the number of hypotheses that I have. And so if I plug that into here, I want m to be at least, just like before, my error epsilon tolerance is that. And now I'm going to do log of this, which we agree is this. Oops, n. Plus the log of 1 over delta, which we agreed was just 1 minus their probability of succeeding is the probability of failing. So there we are. And it turns out I also solved this before class. If n is 4, if we have 4 x1 through x4 features, then m must be at least 184. And if n equals 10, m must be at least 224. And if n is 100, then m must be at least 318. Okay. So you can play around with this yourself, but you see the idea. So we've got a bound, and we can apply it to different learners. To do that, we have to really analyze the hypothesis space being considered by the learner. And the more complex the hypotheses, the more examples we're going to have to show it in order to achieve the same, with the same probability, the same guarantee for the error epsilon. Yes? Oh, I see what you're saying. Yeah, I thought about that. The comment is probably we shouldn't have divided by 2 because I can choose n things for the top level of the tree, and then I still have n minus 1 choices for the second level of the tree. So in a way, we weren't double counting, and I shouldn't divide by 2. Now, here's the interesting point. I divided by 2 anyway, and here's why. I agree with the argument that syntactically, there are different trees if I put x5 first and then x7 for the second layer than if I put x7 first and x5 for the second layer. Those are syntactically different tree structures. However, any function that I can represent with x5 followed by x7, I can also represent with x7 followed by x5. So the semantics of those trees are identical. And so I divide by 2 because what we really care about is the number of distinct functions that can be represented by h. And we're not so interested in how many distinct tree structures. We'd like to not count 2 different trees that represent the identical same function. We don't want to count those twice.
Actually, then you should go even deeper, because if you are counting the different semantics, then all the trees that with all ones on the leaves, no matter what's the xi and xj.
That's right. So this is a very good comment. So the comment is that I'm still overcounting because I'm allowing 16 assignments of 0s and 1s on the bottom of the tree. And of course, if I put 1s on the bottom of the tree,
It doesn't matter.
it doesn't matter what xi and xj are. So I still overcounted. Dealing with all these overcounting issues is a real morass, and I don't want to go into it. And besides, I'm giving a bound. So all I said was that it suffices, if you have n equals 4, it suffices to provide 184 examples. It's an upper bound on the number of examples you need. And so, in fact, if I had just counted the number of syntactically distinct trees, I'd still get a legitimate upper bound. It would be a little bit looser, a little bit higher. And so this is something actually to understand. I'm glad you raised that question, because it is important to understand what's really going on here. What matters is not really the number of syntactically distinct hypotheses, but what matters is the number of different functions that those hypotheses can really represent. So that's kind of cool.
So say you pick a hypothesis space, right? And then you choose like an error and a probability, and you calculate an m.
Mm-hmm.
So if I understand it right, if it misclassifies any of those m training examples, then does it say anything about your like, does the theorem apply if it misclassifies them?
I see. So the question is, what happens if the hypothesis misclassifies a training example? And remember, we very carefully stated that this theorem only applies to a consistent learner, by which we mean a learner that outputs a hypothesis that perfectly fits the training data. So we're really not, this theorem doesn't apply except in the conditions where there is a hypothesis that the learner can output that perfectly fits the data, and it finds it. That's the only condition under which this theorem applies. Okay, let's look. I want to skip over some of this. Let's look at the situation where that doesn't happen. So let's loosen up this constraint. In fact, people call this looser setting agnostic learning, in the sense that what if we don't make the assumption that the learner necessarily has a hypothesis that can perfectly label the examples? Let's not make that assumption. Be agnostic about that. Maybe it will, maybe it won't. So then what do we want? Well, the reasonable thing to want is it should still output the hypothesis that makes at least the fewest errors on the training examples. If the fewest possible is 0 errors, then we'll get what we had been talking about. But maybe there's no perfect hypothesis. The best you can do is find a hypothesis that gets one training example wrong. Okay, if you can find that, if that's the best you can do, then we'll take that. Okay, now what can we say about the bound on the true error in that setting, that more general setting? And now we can't use the theorem that we derived because remember, you proved it. You were proving it by making the assumption that this hypothesis is going to be thrown out of the running if it makes a mistake on any of those M examples. You calculated the probability of that happening. That's how you proved the theorem. So we can't use that. But there is a generalization of this with a different proof based on Hoeffding bounds that gives us an expression remarkably similar to the one we had before. And this one says, in this case, the true error will deviate from the training error by at most epsilon with probability 1 minus delta if we provide at least this many M examples. And this actually comes from something called the Hoeffding bounds, which are a very nice general bound to know about. Essentially, it tells us that even if the training error is not 0, the probability that the true error is more than epsilon from the observed training error, that probability is bounded by this quantity. And so this epsilon is kind of like the overfitting quantity, right? So we have some training error that looks pretty good. The true error could be worse, though, because we might have overfit. How bad can the overfitting be? That bad? Well, there's the probability of the overfitting being that bad. So the Hoeffding bound is very nice. And it gives us a way of dealing with this more agnostic problem setting. Uh-huh. There is no H here. There is an H here. And we have to prove this, and we use this as part of the proof. And we're not doing the proof here in class. But there is an H still here. And to prove that, you have to do, again, you have to consider uniform convergence. You have to consider all the possible bad hypotheses. And this one is considering one hypothesis. So we have to, again, take into account that there might be k bad ones and get a union bound. We're not going to go through that proof, but I just want to point out that this result can be generalized with a different proof to this agnostic setting, which makes it much more interesting, right? Because there are a lot of times when, of course, if you don't know the function that you're trying to learn, then you can't be sure that you've got the hypothesis representation that can express the function the teacher is trying to teach you. You can't be sure. Well, you could be sure if and only if you had a hypothesis representation that could represent every definable function over x. But as we discussed long ago in our big picture discussion, if you have that, then you're going to need, we didn't quite prove this, but it turns out you're going to need to see every training example if you can represent every hypothesis. Can we prove that? I don't want to go there now, because we don't have time. Okay, so this result does generalize in an interesting way. Here's a slide that gives you a little more detail on Hoeffding bounds. And here's the question I want you to think about before next class. We started out with two kind of restrictive assumptions. One was that we had a finite hypothesis space and that it was possible to find a consistent hypothesis. And then we did the proof. Now, we just talked about agnostic learning, which removes one of those two restrictions. So in agnostic learning, we say, well, maybe there is no consistent hypothesis, and so we'll take it if you can output the one that makes the fewest errors on the training sample, and then we can still bound the true error. Okay, the question to think about before next time is, what if we had an infinite hypothesis space? Like we do, for example, in the case of logistic regression with real valued variables. Then we can't use this expression that we had at the top of the slide because the number of hypotheses will be infinite. There are infinite number of lines we can define with a logistic function with the right parameters as decision surfaces. So what would be a good substitute measure of the complexity of the hypothesis space? So next time we'll talk about that, and next time we'll also reserve half the lecture to do a midterm review. So see you Tuesday.